Hi, in this video I'm going to go over acid and base equilibria, and with that, what are weak acids and what are weak bases. So I'm going to start off with the acids. So weak acids only partially dissociate in an aqueous solution. So, right, meaning they're going to have the equilibrium errors. So an example, HNO2 aqueous plus H2O liquid is in equilibrium with H3O plus and then NO2 minus. Because this is equilibrium, we can write out an equilibrium expression just like we would for any other equilibrium. So that expression would be, right, Kc is equal to the concentration of H3O plus times the concentration of NO2 minus over the concentration of HNO2. Right, we don't consider the water in here because it's a liquid, it's pure, it's not in the aqueous form. So we don't consider the water. That is our expression. Now, because we're talking specifically about the dissociation of a weak acid, we can change this from Kc to Ka. So Ka is the term we'll use for the equilibrium constant expression for a weak acid. Now, the larger the Ka, the more an acid dissociates. Right, so larger Ka, the more an acid dissociates. Right, meaning it's a stronger acid. Right, it's not a strong acid because strong acids dissociate 100% in water, but the larger the Ka of an acid, the stronger an acid it is. Right, so for example, I'm going to have two acids here that are pretty similar to each other. So HClO2 and then HClO. The Ka of HClO2 is 1.1 times 10 to the minus second, and for HClO, it's 3.0 times 10 to the minus fifth. Now, if you remember in the video about the pH, right, you take the negative log of the concentration of the hydrogen ion to get the pH. We can also get pKa. Right, pKa is going to equal the negative log of the Ka. So in this case, 1.1 times 10 to the minus second to give 1.96. And then the pKa of HClO would be negative log of 3 times 10 to the minus fifth to give 4.52. So you can judge how acidic an acid is based on its pKa. The lower the pKa, the more acidic an acid is. So HClO2 is going to be more acidic than HClO. Now, because H3O plus or H plus is one of the components of the expression for Ka, Ka is interrelated to pH, or pKa is interrelated to pH. So I'm going to give an example problem here of how, if we're given what the pH is, we can calculate the Ka. So we have a solution of formic acid has pH of 2.38. Calculate Ka. All right. So we're told initially we have an initial concentration of formic acid of 0.10 molar. So the first thing I'm going to do is this pH that we're given here is the pH at equilibrium. Right, that's not the initial pH. That's once you form this solution of formic acid, that's the pH of it. So recall that the concentration of H3O plus is equal to 10 to the negative pH. So that's going to be 10 to the negative 2.38, which is going to equal 4.17 times 10 to the minus third molar. So now if I set up my equilibrium expression, so I have the formic acid plus water is in equilibrium with formate, so the conjugate base, and then hydronium ion as the conjugate acid. Set up the ice table. Right, this is equilibrium, so we're going to be using these ice tables to help us. I'm not considering the water, right, because it's a liquid, so I just X that out. Initially, 0.10 molar formic acid. I have none of either the formate or the hydronium ion. Right, this is minus X, plus X, plus X. And I know the final amount here is going to be 0.10 minus X, X, and X. That value, this is X, right? That's the equilibrium concentration of our hydronium ion. So that means to calculate Ka now, right? Ka is equal to the concentration of formate times the concentration of hydronium over the concentration of formic acid. So this is going to be 4.17 times 10 to the minus third times 4.17 times 10 to the minus third over formic acid is going to be 0.1 minus 4.17 times 10 to the minus third. And this is equal to 0.0958. Right? So I do all of that, I'm going to get an answer of 1.8 times 10 to the minus fourth. That's the Ka of formic acid. So here you can see the interrelationship between pH and pKa, right? And that also means the relationship between Ka and then concentration of hydronium ion. Now another thing we're able to calculate is the percent ionization of an acid. Because weak acids don't dissociate 100%, their percent ionization will vary depending on how acidic it is. So percent ionization is equal to the concentration of H plus at equilibrium over the initial concentration of the acid. So in this example, let's say I have a 0.30 molar solution of HF, and the pH is equal to 2.1. So I have to calculate the percent ionization. So my percent ionization is going to equal, right, concentration of H plus at equilibrium over the initial concentration of HF. Right, this is my initial concentration of HF. Then to calculate the concentration of H plus, it's going to be 10 to the negative pH, right? So 10 to the negative 2.1, which gives me 7.94 times 10 to the minus third. So the percent ionization is going to be then, well, we'd have to multiply it by 100 to get the percentage, right, it's going to equal 7.94 times 10 to the minus third over 0.30 times 100 to give 2.6%. So you see with weak acids, like hydrofluoric acid is incredibly acidic and dangerous to work with, but it only has a 2.6% ionization, right? So it doesn't have to have a large percent ionization for an acid to be acidic and dangerous. Now I want to run through another example here, and this time it's using Ka to calculate pH. So using Ka to calculate pH. All right, in this example, we have a 0.4 molar solution of HCN, and that an HCN has a Ka of 4.9 times 10 to the minus 10th. All right, so I'm going to set up the equilibrium here. Just going to be, right, HCN is in equilibrium with H plus Cn minus. Now notice, I'm not writing in the water here in the hydronium ion. The equilibrium's the same, whether you write it like this or you write it like we did in previous examples with the hydronium, because you don't consider the water. All right, so let's do an ice table. I initially have 0.4 molar HCN and nothing of the hydrogen ion or the cyanide. I'm going to lose X plus X plus X to give me 0.4 minus X, X, and X. So now I can say Ka is equal to the concentration of H plus times the concentration of Cn minus over the concentration of HCN. It's going to equal X times X over 0.4 minus X. Now, a shortcut we can do is I can cross out the X down there. Because if you remember, our Ka is 4.9 times 10 to the minus 10th. That's incredibly small. Meaning the X value is going to be super small because our denominator has to be much larger than our numerator to get a number that small. So the amount of X we're losing compared to 0.4 is so tiny that we can ignore it. And this makes it so we don't have to use the quadratic equation. So now I'm going to get 4.9 times 10 to the minus 10, so that's Ka, is equal to X squared over 0.4. So when I do this math, I get X is equal to 1.4 times 10 to the minus 5th molar. So that means that our pH is going to be the negative log of the concentration of H plus, which in this case is 1.4 times 10 to the minus 5th, and this gives a pH of 4.85. And that answer makes sense. It's acidic because we have a weak acid, but it's not nearly as low of a pH as, hydrofluoric acid was, which had a much smaller or a much larger Ka than the cyanic acid does. So this rule I was saying here with the shortcut, in general, if X is less than 5% of the value of the initial concentration, it can be ignored. So often for these weak acid and weak base equilibria problems, because Ka is very small, you can ignore that change in X. Now, one thing I want to note is you can have polyprotic acids. right? This is going to be multiple acidic protons. An example would be your H3PO4, so phosphoric acid. Each of these protons is going to have a different Ka. So in phosphoric acid, Ka1 is 7.5 times 10 to the minus third. Ka2 is 6.2 times 10 to the minus eighth. And Ka3 is 4.2 times 10 to the minus 13. Sometimes when we're calculating pH, we only need to use Ka1. So if the Ka1 is greater than or equal to 10 to the third more than Ka2, we could ignore Ka2 when calculating pH. So if you were going to try to calculate the pH of phosphoric acid solution, you would only need to consider Ka1 because it's much greater in magnitude than Ka2 or Ka3. Now, if we do need to use Ka2, I'm going to show you like how you would set it up with the ice tables. So an example here, we got H2C4, H4O6. So weak acid here. This is an equilibrium with HC4, H4O6 minus, and then H plus. So the ice table for this is going to be, let's say we have 1 here, 0, and 0. Right, we'd have minus x, plus x, plus x. This would give 1 minus x, x, and x. So if we're given, so let's say we're given the, right, we have to be given the Ka. When we're given the Ka, we can calculate what the value of x is, right? And once we have that value of x, then we can move on to the second ice table we'll have to do, right? So Ka2 would be, right, HC4, H4O6 minus, I'll keep it consistent with how we have it above. So this is an equilibrium with C4, H4O6, 2 minus, and then H plus. So ice table again. So all of the protons that are the more acidic ones are going to dissociate before any of the less acidic ones do. So what that means is that our initial value of the concentration of the HC4, H4O6 minus is going to be X. Right? We have an X amount of it from the previous question. So we have that amount. Our initial value of the C4, H4O6 minus is 0. And our initial value of the H plus is X. Right? Again, we got that from up here. So this time we're going to lose a Y amount of it. I'm going to gain a Y amount, and I'll gain a Y amount. So then the equilibrium value is going to be X minus Y, Y, and then X plus Y. Right? I'm not using numbers here because that would take a lot longer, but I'm showing this is the formula and the structure you'd use to get what the pH is if you have a polyprotic acid where you have to consider both of the Kas. Now, last thing I'm going to mention is Kb, and this is for weak bases. All the same rules follow from Ka. Right, so if I have a reaction of a weak base, say I have sulfate, SO4 2 minus, plus water, to give HSO4 minus plus minus OH. Right, Kb is going to equal the concentration of HSO4 minus over OH minus all over SO4 2 minus. So same equilibrium structure that we had for Ka, it's just this time it's a base that's reacting, not an acid. So we have Kb instead of Ka. Now Kb and Ka are related to each other. Right? Ka times Kb is equal to Kw. And if you remember, Kw is 1 times 10 to the minus 14th. So that means if you know Ka, you know Kb. If you know Kb, you know Ka. Because they're related through this equation. So I know this video was a little longer than most of mine are, but acid-base equilibria is a complex topic, and it takes a little bit more time to go through. So I'll have a couple more videos on acid and base chemistry.